All right, so now let's change track a little bit. We now have our template for our property that we want to get an estimate for. That template is currently populated with the average values in the dataset. So now let's get the estimated theta values for our model. And while we're doing that, we can also calculate the root mean squared error for our prediction interval. I'm going to be using scikit-learn to do this. Let's store our regression in a variable called regr, and that's going to be equal to linear regression. So this is scikit-learn's linear regression. And we can use that linear regression to already fit our values. So we can calculate all the theta parameters simply by calling the fit method on his. And the fit method needs two inputs, namely the features and our target. If I hit Shift Enter, this calculates all the theta values in the background. To get the predicted values or the fitted values, we can use regr.predict and then features. So based on our features data frame, we are calculating all the predicted values using the thetas from our model. Let me store this in a variable called fitted_vals. Fitted_vals now has all our predictions. The next step is calculating our mean squared error and our root mean squared error. And this is where I'm going to throw it over to you. Can you calculate the mean squared error and the root mean squared error using our scikit-learn module? I'll give you a few seconds to pause the video and give this a go. Ready? Here's the solution. The MSE is going to be equal to the return value from our mean squared error function that we've imported at the top. Mean_squared_error needs two inputs, the target and the fitted values. If we output the mean squared error for our regression, it's currently equal to 0.035 approximately. Now what about the root mean squared error, the RMSE? That's simply going to be equal to the square root of the mean squared error. Now I'm going to use numpy again, so np.sqrt parentheses MSE will give me the root mean squared error. The value of the RMSE is equal to 0.175. And the units for both the mean squared error and the root mean squared error are still log dollar prices in thousands. Now we have everything in place to make our predictions. I'm going to delete this here, hit Shift Enter, and go down to the next cell. What I want to do here is I want to create a Python function which will estimate the log house prices for a specific property. We'll get the log prices first, the log estimate using our dataset, and afterwards we'll do step 2 where we convert this output into today's dollar values. Now we've not written a Python function of our own for a little while, so this is a good chance to review this as well. The way you create a function is with the def keyword, def, and then the function name. I'm going to call this function get_log_estimate, two parentheses, and then a colon. Let's have this function return a dummy value for now. So I'm going to say log_estimate is equal to 21. And then down here, I'll specify a return value for this function. So I'll say return log_estimate. Now that we've defined our function, we can use it. We can call it. So get_log_estimate parentheses will output the value 21. Fair enough. So this is pretty much all review. The thing I actually want to show you in this lesson is not just how to create your own Python function, but how to create a Python function with arguments, some of which have a default value. Because once you do that, when calling the function, the arguments that already have a default value are optional. Let me show you what I mean by that. If I come in here into my function definition and I specify an argument, say nr_rooms, and hit Shift Enter. When it comes to calling our Python function, I now need to supply this argument. So if I hit Shift Enter now, I'll get a type error because I'm missing one required positional argument nr_rooms. Calling the function now requires that I have some value for the number of rooms. Only then will the code execute. Let's add 4 arguments to this function total. Number of rooms being 1, the next one being students_per_classroom. So this will be our PT ratio, comma, and then we'll have next_to_river, comma, and then we'll have a 4th argument, high_confidence. And this last argument will be for whether or not we want to have a 95% prediction interval. All right, so now we have 4 arguments, meaning we need to specify values for all of these arguments here. To make one of these arguments optional, say next to the river, I can give it a default value in our function signature, in our function definition. So next to river can be equal to, say, false, and high confidence can be equal to, say, true. What we've just done is made 2 of these arguments optional, meaning we only need to specify the number of rooms and the students per classroom. So coming down here where I'm calling this function, I can have 5 and say 19. And this cell will now execute just fine. All right, so we can't have this function return the value 21 all the time. That's just silly. What we actually want is we want this function to return the price estimate for a particular property. So we're going to use our regression object, regr, and the predict method on that object. And then as an argument to the predict method, we need to supply a single row of features. That single row will be our property stats, which currently hold on to the average values for all the features in our dataset. Check it out. If I press Shift Enter to refresh this cell and then pull up the values stored inside property stats, I can see an array with 11 features and all the average values. Okay, let's see what the log price estimate for this particular property is. regr.predict property_stats. Shift Enter and Shift Enter again. We see that we get an array of 2 dimensions, mind you. It has 2 sets of square brackets, and then we get a price estimate in log dollars. Now, if I wanted to get the raw number instead of an array, we can access that value with square bracket 0, square brackets 0. So first row, first column, Shift Enter, and Shift Enter again will give us the log price estimate of the array. Now, of course, this is fairly boring, right? Because even though we've inputted some values here as arguments to number of rooms and students per classroom, we're not really making use of them inside our function. So I'm going to add a comment here that reads configure property. And then I'll add a second comment here that reads make prediction. When it comes to configuring our property, I'm thinking we can do it in a very, very similar way to the way we did it up here. So check it out. We can make use of this input, the number of rooms, by changing a particular index of our n-dimensional array. So property underscore stats, square bracket 0, so row number 1, and then column number will be rm underscore idx, which is column number 4. And we're going to set that equal to nr underscore rooms. Now we have this number here, when calling the function, filtering through into configuring the feature that we're then going to make the prediction on. So Shift Enter and Shift Enter, you'll see that number change. Now, as I change this from 5 to say 8 to 9 to 3. We can now get price estimates for properties that have the average values for crime and LSTAT and pollution from the dataset for all the features except for one feature, namely the number of rooms. This now depends on the input to our function. Let's do the same thing for PT ratio, the students per classroom. I'll let you pause the video to add that line of Python code. Ready? Here it goes. So property underscore stats, square brackets 0, square brackets, and then it was PT ratio underscore idx is equal to students underscore per underscore classroom. Now we can adjust the valuation of our property based on how many kids there are per teacher. Shift Enter and Shift Enter again, and changing this and hitting Shift Enter again, we can see that for a PT ratio of 10:1, the log price estimate is 3.05. And then for a PT ratio of, say, 20, so a much bigger class, the log price estimate will go down, right? So it'll be 2.68. Brilliant. Now you can see where this is going, right? Next up is this next to river argument that I've given here. This is going to be all about our Chaz variable. Now, Chaz was a dummy variable, right? It's either equal to 0 or it's equal to 1. The way we're going to configure our features is using an if-else clause. So if next underscore to underscore river colon new line property underscore stats square bracket 0 square brackets Chaz underscore idx is equal to 1. New line else semicolon property underscore stats square brackets 0 square brackets Chaz underscore idx is equal to 0. What code did I just write here? In English, this would read, if the property is next to the river, if next to the river is true, then we're going to change one feature, namely the column for Charles River, to 1. Otherwise, if next to river is false, which is the default in this case, property underscore stats for the Charles River column should be equal to 0. The value of this point in our array is conditional on the value of next to river, which should either be true or false. When we're calling our function like so, this value here that we're getting for a 3-room dwelling with a PT ratio of 20, we're getting a value of 2.68. This property here is not next to the river. If I hit Shift Enter on this cell to refresh, and refresh this cell, then we see what this property would be priced at if it was not next to the river. If, however, next underscore to underscore river is equal to true, and I refresh this cell, then we can see the premium of this property reflected in the price if it was next to the river. And that's because, again, living next to the river is a desirable thing. All right, so you can see where this is going. What we've just done is we've created a function and we're configuring the property that we're getting the estimate for using the arguments to that function. So number of rooms, students per classroom, and whether the property is next to the river. For all the other features like pollution and highway accessibility, we're just using the average values of the data set. If we wanted to, we could add more lines of code here and increase the number of arguments that are being supplied to this function to set those as well. But for this exercise, let's keep it simple. Let's keep it to 3 custom inputs. Now, what about this fourth one that I made you add earlier? High_confidence. What I had in mind for this one was to calculate the range. So let's add another comment here and have that read calc range. This is our prediction interval. I'm going to adopt the same pattern. So if high_confidence colon do X, else colon do Y. Now, what am I trying to get at here? If high confidence is equal to true, then I want to calculate the 2 standard deviation prediction interval. I want to calculate the 95% prediction interval. And otherwise, I want to calculate the 1 standard deviation prediction interval, the 68% prediction interval. The prediction intervals, of course, have an upper and a lower bound. So upper_bound will be equal to the log estimate plus 2 times RMSE. Yes, that's our root mean squared error coming back in here. And the lower underscore bound will be equal to log_estimate minus 2 times RMSE. Now, what about if we don't want a high confidence prediction interval? What if we don't want a large range? Well, I can copy these 2 lines and I can paste them in here. And instead of using 2 times the root mean squared error, we can simply use 1 times the root mean squared error to calculate our range. So this is a wide range and this is a narrower range. The last thing I'm going to do is I'm going to make this very explicit. So I'll say interval is equal to 95. And here I'm going to say interval is equal to 68. I'm going to use this variable here in a print statement later on. For now, what we're going to do is return all of these calculations. So check it out. We're going to return our log estimate. We're going to return our upper bound. We're going to return our lower bound. And we're going to return our interval. Hitting Shift Enter, I refresh the cell. And hitting Shift Enter on this one, I can now see that I get a tuple. This is what the parentheses are telling us. And that tuple consists of 4 things. The log price estimate, plus 2 standard deviations, and minus 2 standard deviations for the range, an upper and a lower bound, plus an indication if this is a wide range or a narrow range. In this case, it is a wide range. Why? Because confidence is set to true by default. To get a narrow range, I can use high_confidence is equal to false, in which case we will enter the else block of the function and get the following output. We get the same log estimate, but the upper and the lower bound will be plus and minus 1 standard deviation, 1 times the root mean squared error. And our prediction interval in this case will be 68%. So this is the 68% prediction interval, and this is the 95% prediction interval. Now that we have a price estimate and an upper and a lower bound and a prediction interval, the next thing to do is to convert all of these log prices into dollar values.